Question 2 from the 2025 Higher Physics Examination from the SQA. A technician sets up the apparatus shown to demonstrate the law of conservation of linear momentum. You can see we've got two light gates attached to a computer, and we've got two vehicles which are on an air track. The air track reduces friction as much as possible. The mass of vehicle P is 0.18 kilograms and the mass of vehicle Q is 0.24 kilograms. And as we said, the effects of friction are negligible. In one experiment, vehicle P is moving at 1.20 meters per second to the right, and vehicle Q is moving at 0.64 meters per second to the left. The vehicles collide and move off separately. Vehicle P rebounds with a velocity of 0.76 meters per second to the left. And for our very first mark, it's asking us here to state the law of conservation of momentum. Well, we know conservation momentum law is stated as the following. The total momentum before a collision is the same as the total momentum after the collision, and little small print is provided no external forces acts on the system. So that's your answer for 1 point. The total momentum before a collision is the same as the total momentum after a collision, provided no external forces acts on the system. And the next part is a calculation all about that. It says calculate the velocity of vehicle Q immediately after the collision. Now in all these cases it's very wise to draw a diagram of what's happening. So here we have a diagram here, and this is going to be before the collision, if I can draw it in, before, and that's going to be after the collision here, after the dotted line. So there we've got the two diagrams of before and after. So we just got to fill in the different data for it, and we can slide up again. We can see that vehicle P has a mass of 0.8 kilograms. So we know that's going to be 0.18 kilograms, and we can put 0.18 kilograms over here. And vehicle Q, we slide up, has got a mass of 0.24 kilograms. So it's going to be 0.24 kilograms here and 0.24 kilograms there. So we've got the masses in. Now to put in the velocities, and we have to take into consideration direction. It says one experiment, vehicle P is moving at 1.20 meters per second. So we have to put in there 1.20 meters per second here. And vehicle Q, it tells us here that vehicle Q is moving 0.64 meters per second to the left. And that's this direction here, 0.64 meters per second to the left. Now what happens after the collision? It says vehicle P rebounds with a velocity of 0.76 meters to the left, so 0.76 meters per second to the left. And really we've got to find out what the velocity of vehicle Q is immediately after, and we'll call that V. So now we use our law of conservation momentum, and we just work out the momentum for each of these particular characters here. We know that the momentum P of a moving object with mass m and speed v is going to be mv. But remember also that momentum is a vector, so we have to be very strict in our rules here. Anything going to the right we take as positive momentum, anything going to the left we take as negative momentum. So let's work out the momentum of P before the collision. It's going to be the mass, 0.18, and it's going to be multiplied by 1.20. And that's going to give us momentum before the collision. Momentum, this one here, we have to take it away because it's going in the left direction. So it's got to be a value of 0.24 multiplied by 0.64 kilograms. Now when we do that on our calculator, we end up with the total momentum before the collision. You take this value here and take away this value here, and you're left with a value of 0.0624, and units are kilogram meter per second. So this has got the total momentum before the collision. And we do the same thing after the collision. After collision, momentum mass times velocity is going to be 0.18 for P times, and this time is going to the left, so we have to multiply by minus 0.76, and that's going to give us a negative number there. And then this part here, we don't know the velocity, so therefore it's going to be 0.24 multiplied by v, and we don't know which direction it's going in. We'll have to work that out and trust in the maths. So that's the sort of kind of rule we've got here. We can rearrange this a wee bit to give us a total momentum after the collision. Total momentum after is going to be 0.24v take away, and this bracket here, we multiply it out, we get 0.1368. And that's going to be kilogram meters per second as well, so I'll just leave that out in the big bracket. I'll put a bracket down there and put in kilogram meters per second for the units of momentum. Now comes the law of conservation of momentum. We know that the total momentum afterwards is going to be equal to the total momentum before, provided no forces, in fact, were acting on it. So the total momentum before is this part here, 2.4 v, the velocity we don't know. Take away 0.1368, and that should equal the total momentum before, which is going to be equal to 0.0624. Just left out units for you for the moment in time. So if we rearrange all that equation here, we can get the following. I'll just make it over here. Therefore, we get that 0.24, keep that in this side, should equal, in this case, 0.0624 plus 0.1368. And therefore, we have 0.24 V is going to equal to the sum of that, is going to equal to 0.1992. I'm just keeping the four figures at the moment. So you can see right away we have got a simple equation now, and we can work out what V is. I'll just do it up here for you. V has got to be equal to 0.1992 divided by 0.24. And we're getting a positive number, which must means that it goes that way to the right. And we work that out, we get an answer of V to be equal to 0.83 meters per second. And that's going to be the velocity of Q as it goes away to the right. Question 2 continued. Show by calculation whether the collision is elastic or inelastic. Well, we know in an elastic collision the total momentum before and after is conserved. It's the same. And we know that the total kinetic energy added up before and after is the same also for an elastic collision. For an inelastic collision, the total momentum before and after is conserved, but the kinetic energy is not conserved. Now remember, the only difference here is that kinetic energy is a scalar quantity. So all we have to do is work out the kinetic energy for each of the objects, P and Q, and compare it to total kinetic energy afterwards. Remember, kinetic energy is a scalar quantity, so we don't have to worry about the direction which the actual part, the P and Q are travelling. So here's the situation we have. We have all the information we have with the mass, and we have the speeds, the velocities, and we know for a fact that the kinetic energy EK of any particle or anything moving with a mass m with a speed v is a half mv squared. So all we have to do is work out the kinetic energy of P, kinetic energy of Q, and if we do that, we should have this formula here, this expression. We have a half times the mass times speed squared, and when we add this up, we get the following answer for the total kinetic energy before. So let's write total kinetic energy before, TKB, and that's going to equal to 0.18 joules to two significant figures. That's what we get when we add this sum up here. Now we do the exact same for the after the collision. We work out the kinetic energy, half times the mass times v squared, work out this one here, and work out this one here. And we can see, because it's a scalar quantity, we just need to add all the kinetic energies. And what we get here is the total kinetic energy afterwards. Total kinetic energy afterwards comes out to be 0.13 joules. So we have lost kinetic energy, and the fact of lost kinetic energy means that the kinetic energy is not conserved, which means it's going to be an inelastic collision. So inelastic collision will be our answer for that one. Inelastic collision.